In the realm of particle physics, achieving precise measurements of the Z, W, and H bosons, as well as the top quark, poses significant challenges. The next E plus E collider complex, FCC, must attain unprecedented luminosities to meet these targets. The FCC-IS European Study is currently investigating the feasibility of these challenges, with a cornerstone of the study being the design and optimization of the high-energy booster, HEB. This paper provides an update on the status of the HEB of FCC in light of recent developments in the injector and collider survey. It also offers an overview of ongoing work on longitudinal stability and design robustness in relation to field, alignment, and diagnostics errors. Constraints and effects related to the design frequency of the accelerating cavities, as well as collective effects, are highlighted. Lastly, the paper presents an investigation into an alternative ArX cell design. The FCC is a double-ring lepton collider designed to function as an electron-positron Higgs and electroweak factory, operating in 4 distinct modes: Z, W, H, and TT. The high-energy booster, HEB, serves as the final component of the injector complex, where particles are accelerated to collision energy and adjusted for efficient top-up injection. Due to the short beam lifetime and requirements for top-up injection, 2 specialized lattices have been developed, one for Z and W modes and another for H and TT modes. The performance of the HEB is significantly impacted by magnetic field imperfections, misalignment, and collective effects, necessitating the correction of these detrimental effects prior to finalizing the design. Prior studies have documented the effects of magnetic multipole errors on lattice momentum acceptance and emittance growth due to intrabeam scattering. This paper provides a status report on the advancements in the HEB design, including the examination of longitudinal phase space stability. To achieve a sufficiently large dynamic aperture and momentum aperture, a non-interleave sextuples arrangement has been employed, resulting in a substantial dynamic aperture in the absence of radiation and RF cavities. However, the size of both the dynamic aperture and momentum aperture decreases when radiation effects and energy compensation at RF cavities are considered. The longitudinal phase space stability is investigated by computing perturbation terms in the momentum compaction factor, which can lead to instability in the longitudinal phase space. The extended form of the momentum compaction in the Hamiltonian reveals the existence of secondary RF buckets in the longitudinal phase space, which can interfere with each other and disrupt the longitudinal phase stability condition. The stability criterion for the perturbation term is defined as a function of the desired momentum acceptance, and the lattice meets this stability condition. The location of the primary and secondary RF buckets in the longitudinal phase space is depicted in Figure 1, with the secondary RF buckets situated at a considerable distance from the main buckets and having a negligible influence on particle dynamics. The stability criterion for the variation of the longitudinal emittance, denoted as 1, is defined as 1 less than 2C4 equals 0 to 226, as established in Wiedemann, 2015. This criterion is crucial in ensuring the dynamic stability of the beam. To assess the variation of 1 within a specified range, the initial amplitude of the particles is taken into account. The results, presented in Figure 2, demonstrate that the variation of 1 remains below the stability threshold for the defined range of x, y, 2, 20, 20, 10, 10, m2. Moving on to the orbit correction study, the primary objectives are twofold. First, to determine the permissible tolerances for the misalignment of the booster's components, and second, to evaluate the necessary strength of the correctors to rectify the closed orbit perturbation resulting from machine errors. A comprehensive analysis is conducted, taking into account various types of errors, including random dipole field and roll errors, quadrupole alignment errors, BPM alignment and reading errors, and sextuple alignment errors. The correction strategy employed in this study is based on the methodology described in Ref. Dalena et al., 2023. This approach involves introducing different error types in a gradual manner to evaluate the tolerances for misalignment and field errors on the elements. The results of these tests provide valuable insights into the permissible tolerances and the necessary corrector strengths to maintain optimal beam stability. The orbit correction study is a critical component of the overall analysis, as it enables the identification of potential issues and the development of strategies to mitigate their impact. By examining the effects of various error types, the study provides a comprehensive understanding of the booster's performance and the necessary measures to ensure optimal operation. The analysis presented in this section builds upon the previous discussion of the longitudinal emittance and its stability criteria. The results of the orbit correction study provide a detailed understanding of the booster's performance and the necessary measures to ensure optimal operation. This research paper delves into the optimization of the high-energy booster, HEB, ArXiv in a particle accelerator, emphasizing the impact of magnetic field errors and their correction. Utilizing statistical analysis, the study employs 100 seeds, each with randomly distributed Gaussian errors within 3 RMS, root mean square, values. The findings reveal that analytical predictions align well with simulation data, particularly in the vertical plane. However, there are outliers in the horizontal plane that exceed the analytical limit due to the combined effect of different errors and the function. The orbit distribution corresponds to expectations, with amplitudes in both planes being in the order of magnitude of the MQ offsets, which are the dominant errors. The pattern of the arcs and insertions is also apparent, as errors were only applied on the arcs, resulting in residual orbits near zero in the insertions. The RMS values for each successful seed are distributed around the dashed red line representing one analytical RMS estimate. The corrector's strength distribution indicates that the strengths are contained within the 3 times mean analytical RMS limit. This leads to the first specifications for the main magnet's misalignment of the HEB ArXiv cells being set to 150 meters, with a maximum corrector strength of about 20 mtm, as far as orbit correction is concerned. These values will be confirmed or potentially reduced following a full emittance tuning performance study. Collective effects, particularly resistive wall and intrabeam scattering, are crucial in the high-energy booster due to its smaller pipe radius and nearly 100 km circumference. The resistive wall effect is expected to be more significant in both the longitudinal and transverse planes compared to the main rains, attributed to the reduced pipe diameter. The Wakefield contributions and impedance are anticipated to be higher, as demonstrated by Migliorati et al. 2018, and Migliorati, M. et al. 2021. The possible presence of eddy currents generated by the ramp of the magnetic field during acceleration is another important consideration. Initially, a stainless steel vacuum chamber was proposed to mitigate this issue, but it would have increased the resistive wall contribution significantly. However, due to the low magnetic field in the booster, eddy currents are not expected to be a problem, allowing for a stainless steel vacuum chamber with a copper coating of 1 mm. This design would ensure that the beam only interacts with the copper from about 2 kHz onwards. A copper pipe with a stainless steel strip about 1 mm wide would be a possible fabrication method, but this would introduce an azimuthal asymmetry in the impedance. This contribution, including detuning quadrupolar terms, requires detailed study. Preliminary results for a circular beam pipe made of copper are presented, showcasing the longitudinal and transverse wake potentials of a 0.2 mm Gaussian bunch for copper and stainless steel in Figure 4. The effects of these collective effects on beam dynamics were investigated using the pi head tail tracking code, assuming a transverse emittance of 3 × 10⁻⁴ mrad in the horizontal plane and 1.4 micrometers mu rad in the vertical plane, with an equilibrium relative energy spread of 3 × 10⁻⁴, and a zero current bunch length of approximately 2.2 mm. The longitudinal Wakefield effect is shown in Figure 5, demonstrating potential weld distortion and a slight microwave instability that increases the energy spread by a few percent. In the transverse plane, the Wakefield can produce transverse mode coupling instability, TMCI, which is more dangerous than microwave instability as it can cause beam loss. The instability occurs when 2 coherent oscillation modes couple together. As shown in Figure 6, the threshold is higher than the nominal current, but the safety margin is not substantial. The analysis of intrabeam scattering, IBS, and Wakefields on beam dynamics in the booster reveals significant impacts on energy spread and bunch length during a linear ramp. Figure 5 demonstrates that as the bunch population increases, Both energy spread and bunch length increase, with IBS contributing notably to the energy spread post-energy ramp. This suggests that IBS may lead to an energy spread exceeding the collider threshold, although this requires confirmation through tracking simulations incorporating both wake fields and IBS. Figure 6 illustrates the real part of the tune shift for the first azimuthal transverse coherent oscillation modes, normalized by the synchrotron tune Q0, as a function of bunch population. This indicates potential for collective effects to influence beam dynamics in the booster. Self-consistent simulations that account for IBS and wake fields are crucial, given their impact on bunch length. It is also necessary to evaluate the difference in resistive wall impedance due to the strip's presence, which can produce an asymmetry with contributions to the detuning, quadrupolar, impedance. A machine impedance model must be constructed, and an updated analytical study using MADX is required, as presented in Dalena et al., 2022. The total radio frequency (RF) voltage budget is a critical input for the design of the FCC-HEB accelerator complex, directly impacting operation modes and performance. Calculating this budget involves considering various energy modes and RF frequencies. The total RF voltage budget is determined using equation 3, which accounts for the booster circumference, bunch length, total energy, slippage factor, normalized velocity, RF cavities frequency, synchrotron energy loss per turn, and energy spread. At injection energy, the momentum acceptance is determined by solving equation 4, which involves the synchronous tune and synchronous phase. Table 1 presents the total RF voltage budget for different energy modes of the FCC-HEB, comparing two RF cavities frequencies, 400 MHz and 800 MHz. The results show that doubling the RF frequency reduces the total cavities RF budget required at extraction but increases it at injection, considering momentum acceptance as a requirement. To enhance the dynamic aperture, an alternative optic scheme is proposed, maintaining a non-interleaved sextuple scheme for all operation modes. This approach allows tuning the momentum compaction by modifying the integrated quadrupole strength near a sextuple, as shown in Figure 7. By adjusting the phase advance between the center of the two quadrupoles, this scheme enables better management of collective effects and improved performance in different operation modes. The FCC high-energy booster is undergoing significant developments, with a primary focus on particle stability in longitudinal phase space and control of synchrobetatron excitations. The current HEB optics design is being evaluated for stability against lattice element imperfections, main sextuple settings, and the interplay of collective effects with a realistic lattice model. Simulations incorporating wake field and IBS, as well as synchrotron radiation, are being conducted to understand injection parameter constraints and compare different energy ramping strategies. These simulations rely on various inputs, including accelerating cavities RF frequency, bunch population, vacuum pipe geometry, material and coating, and collider length. To ensure optimal solutions, this study must be conducted in parallel with other ongoing investigations, such as pre-injectors, collider optics, radio frequency, and ArXiv optics patterns. This parallel approach guarantees that all necessary inputs are considered and accounted for. A novel scheme for tuning momentum compaction is proposed, utilizing focusing-defocusing quadrupoles instead of sextuples. This method simplifies cabling and distribution of sextuples in the ArXiv, enables tuning of momentum compaction during the ramp, and is compatible with any ArC pattern, provided the phase advance between sextuples remains 180 degrees. However, this scheme has drawbacks, including the need for an additional power supply for the quadrupoles, a larger equilibrium emittance compared to a photocell with the same momentum compaction, and a potential reduction of dynamic aperture and momentum acceptance. This research is supported by the European Union's Horizon 2020 Research and Innovation Programme under Grant number 951754, FCC-IS. The paper presents a novel approach to quantum computing, introducing the concept of quantum entanglement swapping, QES. This innovative technique allows for the creation of entangled pairs of qubits without direct interaction, potentially revolutionizing quantum communication and computation. QES is based on the principle of entanglement swapping, where two pairs of entangled particles are created independently, and then their entanglement is swapped through a series of quantum operations. This process enables the creation of entangled qubits that have never interacted, which could significantly enhance the efficiency and scalability of quantum systems. The authors describe the theoretical framework underlying QES, detailing the necessary quantum gates and measurements required for successful entanglement swapping. They also provide an analysis of potential sources of error and propose strategies for mitigating these issues. A key aspect of the paper is the experimental demonstration of QES using photons as the quantum information carriers. The authors report successful entanglement swapping between two pairs of photons, resulting in the creation of entangled pairs that have never interacted directly. The implications of QES are profound, as it could enable the development of highly secure quantum communication networks and more efficient quantum algorithms. Furthermore, the technique may open up new avenues for exploring the fundamental principles of quantum mechanics. However, the authors acknowledge several challenges that need to be addressed before QES can be widely adopted. These include improving the fidelity of entangled state generation and enhancing the efficiency of quantum gates and measurements. In conclusion, the paper presents a groundbreaking approach to quantum computing that has the potential to significantly advance our understanding and utilization of quantum systems. While there are still technical hurdles to overcome, the prospects of QES are promising, paving the way for a new era in quantum technology.